All right, so how you guys doing today?
Good, how are you?
I'm good, perfect. Thank you for asking. All right, so I don't know if you guys watched the Monday lecture. We talked about the last part of chapter 3. So I'm gonna do this again. We learned about the confirmation. Confirmation. So simply means this is done by rotating the single bond. Okay. So any change it makes the different structure by conformation, meaning they made a difference in the structure of something by just rotating the single bond. Okay. So meaning if you have a single bond between these two carbons, you can actually rotate it. Okay, that's okay. That's no problem. But I say single bond here specifically because if it's the double bond or triple bond, it cannot be rotated. Okay, so only single bond is the one that we can assume they can be rotated. Okay, makes sense, right? So this is why if you look at the ethane, if you look at the ethane. If you look at the ethane over here, we have two carbons, obviously, and we have 3 hydrogen over here. Okay. So maybe we can put it in more nice way. We can actually put this in the wedge, okay, and we can change this to dash line, okay. Looks like this. So if you see the line, just a regular line that's drawn on this board, it's just parallel to the board, the 2D you're looking at right now. So those are ones, 2 carbon-hydrogen bond on those 2 carbons are also on this plane. Okay? But the one is on the wedge, meaning it's actually going forward like this way. So those 2 are actually heading toward to you. Okay, these 2 bonds, and the dashed line is going back side of this board. Okay, so it's going toward to the other direction over there. Okay? So this is the regular way, normal way for us to present the 3D structure of the organic compound. But sometimes this is not good enough. So what we normally do instead of if this is not working so well for explaining some confirmation and so on, is the first one is Hull projection or representation is what we call. So we try to kind of look at this not on the front like using wedge and dash line, but we just looking at from like a top 45 degree up and to the and from the side. So if that is just something you can see over here. We try to look it up from up 45 and to the side. So maybe I can show you like this. This way. So now you're looking at in the front over here, right? You're now looking at to here. Make sense, right? So you're looking at in front right here, this one, but to here is what it looks like. Okay? So this is what we call C-Hall representation. So you can actually tell what is the bond angle from this carbon to this hydrogen, and also the one on the back, carbon on the back, and hydrogen here. So as you can see, this is not a good way to, this is pretty good, but not so ideal. So what we actually do use the most is the Newman projection. Newman projection. So that is this carbon come to in a dot. Okay? And then you just draw this bond angles on carbon-hydrogen bond to each other. So it'll be here. So this little dot over here is a carbon. We just don't say it. Okay? And the carbon on the back will be circle like bigger circle. So this carbon is on the back. This is the carbon here. And then draw this bond angle to the carbon on the back into this way. So you can actually tell much easier in this way what makes the bond angle from here and here, one here and here, here and here, here. It's much easier in this way. If you really want to know what's the bond angle difference between the carbon-hydrogen bond to the front side and the back side. Make sense, right? So obviously this is a much better way to say it, okay? So if that is the case, like I said, you can actually rotate the carbon, right? So if you have, I'll just draw it nicely now without any, I don't know, it's much easier this way. So here's the thing, I understand what's the bond angle between carbon, hydrogen, it's tetrahedral structure, right? So it'll be 109.5. But that is the bond angle in what? 3D, right? But if you put it all bonds on in front of you in the 2D plane, it will be just merely what? 120. Because we put it in the 2D, not 3D. Okay? So those ones has a 60 degree apart. Just for this one. So technically speaking, there are 109.5, but in this Newman projection, it will be 60 in the 2D projection, right? Okay. So here's the thing. If you think about this one here, they're evenly nicely stretched out from this 2D, or you can say 3D place, but in 2D wise, it's a 60 degree apart from the carbon bonds on the front and back. Then this is very stable, or I can say more stable than this one. This one, okay? So if you think about the distance between those hydrogens are closer here, okay? So this is more stable, less stable, okay? And we're gonna call this staggered conformation. So what I just did over here is we just rotated 60 degree. Okay. So if you just rotate 60 degree, that's what you're gonna get in here. And before we do the rotation, it's a staggered conformation, which is more stable, and this is less stable one. We call this eclipsed conformation. Eclipsed conformation. So does it make sense? Okay, perfect. So if that is the case, so what they really mean is this is the one that experienced the more discomfort, the ones of the staggered conformation. So normally the discomfort is about 4 kilojoule per mole. You don't have to memorize the number, but just there might be certain. I'll give you a number. I'll tell you right later. So this amount of energy is required to put this staggered conformation into eclipse conformation. Because normally, if you're the compound, you don't want to experience the discomfort, right? But if someone tried to force you to put it in the discomforted position, you have to. And that is the amount of the energy that makes it forced into the eclipse the conformation. So in nature, if you have a lot of ethane in the space, you have a lot more of what? Staggered conformation than eclipse, because they don't want to do this one unless they have enough energy to do so. So that's the amount of energy in here. And this is the So this is the, okay. So this is more stable. So if you want to have a certain name for this amount of the discomfort, we actually call this torsional strain. Meaning, torsional means you're twisting it, rotating it. And this is the amount of energy that will force this compound to rotate. So strain is just like the force, like things you can put on more. So we name this torsional strain because this is the one that can be forced to be rotated. So we call this this amount of energy requirement is what we name torsional strain. Because we have to be forced to rotate. Okay. Can I move on? Okay. So it's all the same here, but I'm just gonna switch the ethane to propane. So propane has 3 carbons, right? And then here, I'm just gonna switch one of the hydrogen on your front carbon to methyl group. If it's propane, there has to be 3 carbons, right? So this is still your front carbon. This is still the carbon on the back, but I'm gonna change this one to methyl group. Okay. So if you rotate it 60 degrees again, okay, you will have also eclipse conformation, right? But the difference here will be what? This is a methyl group, perfect. Oh, so meaning this still be the same amount of energy is required to make it forced to be in that eclipse conformation position, but this will be even greater, right? It's about 6. Okay, so now you see this. To make this propane into the eclipse position like this, you need to have even more energy. So it's not just about it's a position anymore. It's not about just simply rotating, but also what? The methyl group. So difference between just the one hydrogen and one methyl group is obviously size. Okay? It's also more bulkier too. So if it's obviously, if you're competing for this limited space with a bigger person, you have also even bigger discomfort you're experiencing on the spacing problem. So this is the same as for the compounds. This is bigger, so there'll be more, bigger amount of the discomfort they're going to experience than just between hydrogen and hydrogen. So this is why this number, particularly in this position, is bigger. So it does have a torsional strain in eclipse conformation, but also on the top of this one, it also has static strain. Meaning, in just the way they're positioned, it is really bigger than just regular hydrogen. They give us more additional discomfort on this position. Kind of makes sense, because it's bigger. So they have a more spacing problem there. So not just simply the location now, because it had the hydrogen had only 4, now it has 6. So there's an additional force they kind of try to go against to resist the position. That's what we call static strain. It's just because of the size. It's much bigger. So rather than just the regular hydrogen, they will have an even higher discomfort. That will show you even higher energy to make this propane into eclipse conformation than one of the ethane. Okay. So far so good. Yeah, go ahead. Oh.
You go ahead.
Yeah, go ahead.
Well, on what we just looked at,
Mhm.
the model of propane, correct?
Mm-hmm.
So how come both of the carbons in the model still have
Mm-hmm.
3 hydrogens coming off if the next one back should have only 2 hydrogens?
Oh, the one in the middle is the one has only 2.
Okay.
So this is right. This one still has the 3 in the terminal carbon. Perfect. Yes.
Can you repeat repeat the definition of the, is it steering?
Uh-huh.
Steering?
Static.
Yeah.
So static strain simply means this one. So we're comparing this one to ethane, right? So this is coming from how you rotate it. So this is how you from rotating your single bond.
Yeah.
But if you do the same thing for the propane, this number will be slightly higher. So it's not just about the position. It's also about the what group you have on the carbon.
Okay.
So if that carbon has even bigger compounds, then we'll have a even higher discomfort that we'll experience. So here's the thing: if there's something you might experience even higher discomfort, this is something you don't want to do even more, right? You don't want to compete with the much bigger groups in the limited space. So that's why it causes even higher energy. So to explain that, we add a top of the torsional strain. We also add a static strain. Sounds good. Perfect. Those are two really good questions. If that kind of it's a lot of things to understand. I totally understand. But if you do have any question, you can also ask me at the class. But I think at least we have some good idea, though, right? Yeah. So how about how about we try to use butane? Okay. So I'm gonna put the two inner carbons in front and the back. So in this case, I'm just gonna tell you. This would be the best way to put it, because I'm gonna tell you why. But if you put it in this position, this is the so you have a methyl group on the front carbon, methyl group on the back carbon is on the opposite direction, right? We call this stagger conformation, but it's more stable form. So we call this anti-conformation. Well, you can say anti-stagger conformation, it's okay. But this is the most stable form, okay? And then if you rotate it 60 degrees, what happened to this one is, let me see, this one have this one, right? Okay. Okay, and this one will have this one, this one. I don't know if I did it right. Yeah, I think right. So if we did this, could you guys remember this was what? 6, right? 6? 6, okay. And this is what? 4, perfect. Nice, great. I'm so excited. So this is 6 plus 6 and 4, right? So in total, you're going to need about what? 16 kilojoule per moles of energy to make it happen, right? We good? Okay. So, and we're gonna rotate this one also another 60 degree. Okay. So remember this number. You don't have to remember the number for the exam, but I just want you to compare the number two. Okay. See. And then if you do the another 60. Okay. Here. Oh, sorry. So just remember. So yeah. So if you do this, now it's also what? Staggered conformation. They shouldn't experience much of discomfort. But think about, even though this is a kind of a 6 degree apart from the front and the back, obviously it'll be, in 3D it will be even larger, but anyway, that case, even though they're in the staggered conformation, because of their size, so the you know, I just drew in this way, but what it looks like is this. Let me see. Yeah, this is what it actually looks like. Okay, so because of its bulkier and bigger than regular hydrogen, even though they are 60 degrees apart, which will have a nice staggered conformation, still slice, very small discouplers still be generated, even though, because they're close to each other. Okay? This is why I put the anti-stagger as most stable, because they're actually opposite direction here. So if you do this, you still have a little bit of discomfort, which is the 3.8 kilojoules per mole. So we named this specially too. We call this gauge conformation. So it's not gauge, it's gauge conformation. It's just because of the nature of the method group. It's much more bulkier and also the bigger. So even though it's in the staggered conformation, especially for butane, it will have a gauge conformation. So they will still have certain amount of discomfort because of that. Okay, kind of makes sense, right? Okay, good. So obviously, the worst thing will be this one. The worst one is these two are in the same position, right? I know this will be quite, a lot of things to memorize, but please let me know. Okay, so in this case, I'm sorry. In this case, we know those two hydrogen 4. This is the 4. Okay, and this one is 11. I think I already explained enough why. Okay, because they are in eclipse position, a conformation position now, and even these two really big bulky group are on the same position too. So it will create the maximum possible discomfort you can have as a butane. And even though you have a nice, some okay discomfort 4 and 4, this will have a very, very high amount of the discomfort. I saw about the 11. So in total, it's going to be 19 kilojoules per mole. So even higher than 16 we saw before in other eclipse conformation too. So this is the most unstable conformation of the butane. This might be the best conformation. Okay. That's it. Yeah.
Are the kilojoule per mole numbers always going to be like if it's 2 carbons like that? Is it always going to be 11 kilojoules per mole, or is that just like for the example?
There should be most likely always 11 kilojoules per mole.
Okay.
The one thing I want to add, we're going to cover this later too, but so this is the amount of energy they need to have to make this conformation change, right? The thing is, you definitely see more of this one for sure. Not so many of this one, but in reality, you also have quite of this one too. You feel like there'll be only very few, but actually quite a lot there. Do you know why? Do you know why? Number seems very big, right? But, well, do you guys remember what we talked about the temperature? What does temperature mean again?
Kinetic energy.
Oh, kinetic energy. Before that was what? Before you transform into kinetic energy, it would be still heat energy. So temperature simply means what? Heat energy per unit volume. This is how you measure the temperature. So we're not living in an absolute zero condition. Obviously, we'll all die. But in room temperature, you still have a lot of energy available to this compound. So they can sometimes easily overcome this discomfort, so they can still rotate if it's single. But maybe not so much, because they still wants to be in the lowest possible energy state, as we all human. Okay. All right. So can I move on? It makes sense. We good? All right. So what time is up? Good. So the next part is the chapter 4. So also we need to start with the nomenclature. There will be first part of the chapter 4. So that is for cycloarcane. Cycloarcane, meaning we're gonna just run about how we're gonna name the ring structure instead of just the linear shape. At this time, we're gonna do the ring structure of the compounds and how we're gonna name this. So if you have something like this one, just quick review. Okay. So we have. Can you guys name this real quick? So the first thing you need to do is what? Find the longest.
carbon
Perfect.
chain.
So how many are there?
5.
5. Perfect. So it'll be pentane, right? Perfect. Good. But you have a alkyl group there, which is additional to your base. But there's only one carbon, so it'll be methyl. Perfect. Great. Okay. And then for locant, you just need to locate it where it is. No matter how you count the carbon, it still 3. So this is what we did in previous chapter 3. Okay. And then we're gonna just do how you're gonna name this one in the link structure. So if I give you one example here, let me give you this one first. I think this will be the okay. Let's start with this one actually. Just the one here. So all you need to know is just once again, it's pretty much the same what we did for chapter 3. Just each corner, each dot will be carbon. So there will be 4 carbons there. Okay, and then I'll just if you try to count the carbons in the ring structure first, and the one is not. Okay, so separate it. Just count the numbers of carbon, one in the ring, or the one outside of the ring. Okay, so there's the 3 carbons here. There's 1 carbon over there. Okay, so in this case, in my opinion, or well, most of the opinion, this is most important because this is much bigger base it can be, right? So in this case, I'm gonna set this one as a base. Okay, this is my base. Then you just need to count the carbon. There's 3, so it's a propane, right? Sorry. Propane. And then it's in the ring structure. So we call this cycloarcane because you only need to do additionally cyclo in front of it. So it's a cyclopropane. Okay. And then if it's a cyclopropane here, and then you just need to add this one as an alkyl group, which is one methyl group over here. So what I'm gonna do is the methyl cyclopropane here, and then maybe you can count the carbon 1, 2, 3 here. Okay, maybe 1, 2, 3 over here. So you can have 1 methyl cyclopropane. Okay. If you do this, it is actually okay. It is actually okay, but you don't have to do this one if there's only 1 alkyl group, because unlike the ones in the linear, so linear has what? First and end, right? The ring structure, they don't have an end point, right? So it's slightly different from the one and the just regular linear alkane. So if I just say methyl cyclopropane, people already know automatically this is on number 1 because there's no end. You're not gonna count the carbon like 1, 2, 3. Why would you do that? You always want it to follow the low one. And if I just say this methyl cyclopropane, people just know, oh, that's where the methyl. There's no point indicating where the methyl group is. So if I change this one to here, it's still the same compound. It makes no difference. Because it's a ring structure. It's slightly different from the regular alkane. So if you have only 1 additional group, you don't have to locate it. I mean, you don't have to. I think if you do, I think it's okay, but I don't know why you have to. I mean, people already know anyway, right? Kind of makes, yeah.
Does cyclo, do we always use that for the ring structure?
Always use it for the ring structures. Perfect, that's a good question. Makes sense, right? Okay, good. All right, so I give you this example. So, how about this one? You have maybe even bigger. Oh, even bigger, like a group over here than the ones on the ring. Okay, so it's pretty much the same 3, but it has 4, right? So in this case, you can put this. You feel like this is more important for you. Okay, so because it has more carbon as a base, potential base. So I'll choose this one instead at this time because it's much higher in the numbers of carbon. So it'll be butane, right? 4, so it'll be butane. And so I'm gonna put this in the like alkyl group. So this is the same. So just put this as a cyclopropane, right? So cyclopropane, but what? Oh. Cyclopropylbutane. And once again, yeah, I don't think you have to name this one. Locate this one because either and will be just the one anyway, right? So oh well, wait a minute. No, we can say 1 because you can put this one on here. Yeah, so we keep 1 cyclopropane. So if that is the case, you putting more importance on the linear shape of the compounds than the ring structure. So basic rule, I'm gonna say this very carefully because the basic rule is that you count the one in the ring, the one without the ring, right? And if that is higher, you can do this in this way. But this is a general rule, okay? But if you do still put this as a base, it's sometimes okay. If you actually Google 1-butyl cyclopropane, or you can say 1-cyclopropylbutane, they are the same compound still. But general rule is the numbers of carbon. So in chemistry field, they're normally okay actually. But if you have to choose one, it will be the better one. Okay? Do you know why? Do you know why we're making this confusing like idea of naming compound? So whenever we try to name the compound, the most important thing is its function. So this is why whenever you name the compound, usually the last part of your compound is a suffix, where you put the functional groups or double or triple bond that makes totally different nature of the compound. But in this alkene one, it's kind of tricky. But if you still think like the ring structure is more important for certain chemical reactions, but you did some chemical reaction with this one, and you had the carbons on the ring structure did something for the chemical reaction, then this is not so important for that chemical reaction, right? Then, as chemists, you can say, oh, this is, I think, 1-butyl cyclopropane to me. Okay, so they use it that way. And also, numbers of the difference is not so much. It's just 1 carbon away, right? So that's possible sometimes, but the general rule is this one. Okay? So if you see sometimes 1-butyl cyclopropane somewhere, it doesn't mean it's the wrong name, just the way it is. But this is the regular way to do it. Okay, makes sense. I'll move on. Yeah.
Why did you add the 1 again to this
Oh,
one?
so if I can put on here.
Okay.
Yeah. So
Okay.
I just thought about but the point, this one. But can I move on? All right. So let's try to. Let's do one more. Okay. Let's try to do one more. 1 or 2 more. Okay. We have about 3 minutes. So if we have this one, so let's try to name this one first. This will be 6 carbon, right? So the hexane, perfect. And then its ring structure will be cyclohexane, perfect. There you go. Okay. Cyclohexane. So if that is the case, now we're gonna do how about we have 2? Okay, 2, not 1, 2. In this case, you have to locate it because there's now not just 1, so you can just start with 1, 1. But now you know there has to be located relative position to another. So in this case, now you don't have to worry about the numbered carbon any much more because I think you guys already know this from chapter 3, but you're not going to count carbon from here, right? I hope you're not, because like I said, we always try to find the lowest possible number combination for the locant. But either way, it's actually fine for this one. It's 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. It's still the same, right? So anything you really have to do for this one is 1, 2, right? 1, comma, 2. And now there's a 2, right? It's a di, methyl, okay? Cyclohexane. So that is, it's not so bad, right? We just had pretty much the same job we did for the arcane, but just in the ring structure, okay? So I'll do one more, and I'll do this again, I promise on Friday, but don't worry about it, okay? So if I change this one to ethyl group, okay? What happens? Now you have to choose the way to number the carbon now, because it's different group now. You have a 2, but these 2 groups are different now. So you have to put some priority between these 2 now, okay? So it's pretty much the same. Okay, it's pretty much the same with the one we did for the arcane. This is ethyl, this is methyl, right? So we still follow the alphabetical order. So at this time, there's only one way to number the carbon, which is coming from ethyl group position. 2, 3, 4, 5, 6. Okay? So this will be not 1 methyl, 2 ethyl. It is going to be 1 ethyl, 2 methyl cyclohexane.
Can you explain that again? Why
Yeah.
you started from?
Yes. So you have 2 alkyl groups, right? You have 2 alkyl groups here, but you have different groups on it. So in that case, we're gonna choose the priority between these 2, which we normally do with the alphabetical order. So ethyl start with E, the methyl start with M. So E comes first in alphabetical order, then M. So we actually gonna put this first. To do that, I'm gonna count the lowest possible number for ethyl group first.
I remember that.
Yeah, oh, perfect. All right, so we don't have time because we had to do extra credit today, but I'll promise you I'll do this again on Friday, okay? Don't worry about it, we'll do this again on Friday, okay?